Okay, recording is working. You guys ready?
Yep.
Okay. Sorry it took so long because I was trying to set up a dual screen thing, and the screen recording part, I have never tried it with a dual screen, so I think the coordinate system, is a little bit different than using the same screen, and my Perl script, does not know how to deal with it yet. So anyway, I prepared a few documents, for just for this. The first one, these are all, from my website. I can give you guys the URL, or you can just copy that. One thing you can also do is just go to drtak.org/teaches/modules. It lists everything that I have written so far since maybe 2004 or so. I cannot remember, when I wrote the first one. You can probably just click on it and find out. Let's see, you can find out pretty quickly. So this one was written 2006. So from 2006 to right now, there are about 200 something modules. But I will only point out the ones that are related to what we will talk about today, and also possibly for the next few weeks. I brought it up already up here. One talks about PCB or printed circuit board design basics. Can you guys hear me all the way to the back? Because I know my voice does not project. So it's good. The other one talks about designing an embedded system controller. And then the last one is a lot more specific. It talks about the different components on an embedded controller, and what is a regulator, how do we use capacitors, and so on and so forth. So it all depends on what you guys want to do. If you just want to know how to design a printed circuit board, but not in the context of microcontroller units or embedded controllers, we can do it that way too. I think it is better to have an objective in mind so that we know what the circuit board is supposed to do, and then we start from there. I mean, it's up to you guys. You want to start with a specific target, like, we want to make an embedded controller, and then start from there. Sort of.
It's easier to start with control. Start with the circuit.
Start with a circuit?
Yeah.
But the circuit has to have some purpose. I cannot just kind of throw something on the schematic capture. How about this? We will start with this particular slide. You can always make it bigger. And what we'll talk about is, first of all, what is an MCU? It's a microcontroller unit. It's basically a computer on a chip. The cost of an MCU can range anywhere from 50 cents, 75 cents each, all the way up to maybe 10, 20 bucks each, depending on how much processing power you want, how much space you want for the program space, and how much space do you want for variables, and etc. The processing power of these things is not really that good, but even at 16 megahertz, they will outpace the original IBM PC-80 easily, while consuming only 0.1 watts. So that's pretty, amazing, how little power it consumes as opposed to how much processing power it gives you in return. Any questions? I mean, if you guys have any questions, just stop me anytime you want. So just, overall topics, about, designing something. Read the fine print, or read the fine manual. It's very important. Because unless you want to have smoke coming out of a circuit board, it is really important to find out the tolerances and all the specifications of the components that you plan to put onto the printed circuit board. Most software people don't have to deal with this because there's no such thing in software, and if you do not write your programs according to specifications, no smoke is going to come out of your PC. But in electronic design or PCB design, if you put in the wrong part, very bad things can happen. So read the manual, and there's a lot of stuff to read. Some of these manuals have more than 300 pages, so it's not light reading at all. And everything starts with a power supply. When you read the documentation of an MCU, it will tell you what kind of power supply it expects. In other words, what is the voltage that you have to supply, and also how much current it is going to consume. How many of you have taken the physics class, like the electricity physics class, where they talk about, current, voltages, and whatnot, resistance, that sort of stuff?
I think in the electronics class we talked about it.
Okay. But don't you guys have to take a physics class
Yeah,
with
that's next
electricity?
semester for
It's
me.
the last one.
The last one. Very good. We can skip a whole big section now. Okay, so all of these are very important things, Okay, let's just kind of jump to the PCB or the schematic capture software. This is a G-Scheme, which is open source, so it is free, 100% free. You can use it. You can use it to design relatively complex designs. There's also a companion product called PCB that you can use to actually design the PCB. There are several stages to designing a printed circuit board. The first part is to identify logically what components do you need and how do you connect the components. And that's what G-Scheme or the schematic capture program is useful for. So one of the things you can do, or one of the first things you need to do, is to look through the components and find out, what you need, and just kind of use those components. And let's see. Okay, it is picking up some of the symbols that I have created. Symbols each symbol represents a particular device. But when you look at a symbol, I can click on one, you can look at the preview. You can see that the symbol does not really represent the physical configuration. That's because a symbol is really only representing the device from a logical standpoint. All it really cares is how many pins are there on the device and what are the labels of the pins of the device. In this case, we have a header, which has six rows and 2 columns when you look at the right-hand side. And all it does is to serve as a connection point to the outside world. You can also look at some of the other, symbols. Like this one here is a MOSFET. So the D's, D1, D2, D3, and D4, they stand for drains on a MOSFET. The G stands for gate, and the S stands for source. Those are specific points or specific nodes for a MOSFET. And that's basically what a schematic symbol is. It is just logically representing a device without actually displaying the shape of the device or what it will look like on the PCB. Any questions about stuff like this? No questions? So for our particular example, you can pick a processor, and we have the ATmega 128, and you can see the ATmega 28 is a very complex type of device. It has 64 pins, and you can see there are 64 pins on that thing right here, and each pin has the necessary caption to show what it is for. So let me just paste it onto the design so that you can see better, what it looks like on the design. And in most of these software, like schematic capture software or PCB layout software, the user interface is not what you expect. In other words, they don't have the zoom control like most software. In this case, we use the lowercase z to zoom in and uppercase z to zoom out, which is not very intuitive, but that's the way they usually write these software. What we really want to know at this point is what do we do with these lines here. VCC is basically the supply voltage, and the ground refers to the ground, which is 0 volts. In other words, how do we power up a device like this safely and reliably? Any questions? No questions? I think it will be much better once we understand the physics of electricity, because a lot of the discussion have some components of electronics to it, but we can just kind of go through this, kind of quickly.
What's the difference between AVCC and VCC?
AVCC stands for analog VCC. In other words, that part is only fed to the analog portion of the MCU for for analog to digital conversion. I can also explain some of these pins here. PA1, PA0 up to PA7 simply means port A, pin 0, port A, pin 1, port A, pin 2, and so on. And this particular device has everything up to PF something. If I remember, there's a PG2. So there are a lot of pins that you can connect to. Some of these pins, or most of these pins, are binary. In other words, they can serve as an input, as a binary input pin. They can also serve as an output pin, as a binary output pin. As an input pin, they can detect whether the voltage at the pin is below a certain threshold or above another threshold. And that's all you can say is below this threshold, it reports in as a 0 in software, or it is above a certain voltage, and it will be reported as a 1 when you read it in software. In other words, you can give it some voltage, in the range of 0 to 5 volts, which is a typical range, and it can detect whether it is close to 0 or whether it's close to 5, but it can't tell you it is 3.6 volts, for instance. For that sort of thing, you need to go to the ADAX or the ADC lines. ADAX stands for analog to digital conversion. It basically looks at the entire range of voltages, like from 0 to 5 volts. It chops it down to 10,024, individual segments in this case, because it's a 10-bit ADAC converter. And so it can, to a certain extent, tell the voltage of actually at the pin, but it's quantized, which means, it can only go by 1,000, in this case, of 5 volts. In other words, 5 millivolts increments. Any questions? Any questions? Okay. We also have, let's see, what is the other important pin here? Another important pin is the reset pin. The reset pin is basically the reset button of an MCU. Remember, this is a computer on a chip. It does not have a button, just for resetting. It has a pin, for the purpose of resetting. When you see a slash in front of a symbol, it means the pin is using quote-unquote inverted logic or active low logic. Most of the time, especially in software, we associate 1 as a high value and we associate 0 as a low value. So when we look at a circuit diagram, we would also think that way. When I want to reset the board, I want the reset pin to experience a high voltage. And if I don't want to reset the board, I want it to be a low voltage. But in reality, it's exactly the opposite. This is called an active low type of signal, which means when the voltage is low, it is asserted, it is active. Okay, and that's what the slash is for, is indicating a pin is active low instead of active high. And are there any questions? No questions? Okay. So the next thing we want to do is to figure out how to power up, an MCU like this. There are several things we need to do. The first thing is to understand what is a voltage regulator. You don't want to blow up, an ATmega 128 because it's $10-15 each, and it's a big hassle to desolder one of these things from a circuit board because it's a surface mount component. You can do it. It's just not very easy. So what you need is a linear regulator. So once again, we go to the library to look for a linear regulator. This particular software is kind of handy because you can type in the name or the part number, and it will automatically search for components with that component inside the name. In this case, it is all listed under linear technology, and when you click on the symbol, this is what a linear regulator looks like. So we'll go ahead and put it onto the board, and then I'll show you guys how to make connections. So we'll just put it right here, it's good.